I have changed up my linear search just a little bit. And I want you to pause the video here and in the comments tell me what is the invariant of this version of the linear search. That exercise worked really well with the original linear search, but I changed this linear search up a little bit. So pause the video now, take a guess, look at the code. You might be completely wrong, but I appreciate it. Drop it in the comments. What do you think the invariant of this linear search is? Go. I hope you were laughing as you read this code. I make a random number generator, and then we're going to iterate over all the items of the array like we did before. But then in here, instead of testing the value at index I say, go give me a random index. Okay, max out at the array.length. Give me an index between 0 and the array length. We'll call that the suspect index. You're suspect until proven innocent. All right, if the array at suspect index is equal to target value, return that index. Otherwise, keep going. Look. Okay, I got bad news. This algorithm has no invariant. There's nothing that's true every iteration of the loop. You could try saying, well, okay, the value that was at suspect index is not the value I'm looking for. Okay, but on the next iteration of the loop, you don't have that previous suspect index. How are you going to fix that? I'll tell you what, don't blink, I'll fix it. Okay, here you go. I've added this array of booleans. It's tested indices, and booleans default to false in Java. So I can say if tested indices at suspect index, if I've already tested that indice, forget it, continue. Otherwise, mark this one as tested, go ahead and test it, yada, yada, yada. But now I just added extra space, all right? Remember, we're going to measure time and space with our algorithms. A Boolean array takes up extra space. And even though it feels like I could probably add an invariant on top of all this, I can't because not all indices will be tested. For example, let's just say suspect index, the very first one comes out as a 2. Let me draw the array out here. There, you can see our array with the values in here. You can see the indices up here. And oh, look, extra space. We had to add all this extra space for our Boolean array just so we can make sure that the indices that we've tested, we don't test again. All right, let's come back up here to suspect index. We say suspect index. Randy, give me an int. Let's say Randy returns a 2. All right, so I'm going to come up here and say suspect index is 2. Have we checked it before? No, but we're about to, so we're going to change this F here to a true. And then we go and we check it, and 6 is not equal to 1. We're looking for 1 right now, so no dice. All right, reiterate. Hey, Randy, give me another int. Okay, yeah, I got one for you. And let's say Randy this time gives us a 2. All right. Well, we've already checked 2, so forget that. Hey, Randy, give me another int. And Randy pops out and says, yo, 2. I got a good Dilbert cartoon for you here. Tour of accounting. Over here we have our random number generator. 9. Are you sure that's random? Well, that's the problem with randomness. You can never be quite sure. All right, yeah, anyway, sometimes I feel that way about my random numbers. Now let's say we're terribly unlucky here, and Randy returns 2 all the time. Well, you know what? We're going to stop at the array.length. We're still iterating over 8 values here. So, hey, once we get to 8, some of the values won't be tested. Too bad. Guess what? We can't have an invariant with an algorithm like this. Now, you're probably thinking, Jamie, you're really beating these invariants, but they're so critical. We're going to use them in every single algorithm, and I had to point this out. That even with the linear search, which, by the way, this is no longer a linear search, but we'll get into those technical details later. But even with a search, you can mess that up where you no longer have an invariant. And now I can no longer prove that my algorithm is correct. Key point. Remember in the previous video how we checked for correctness? We can say, yes, we've checked every single value, and we either know the index of that value or we know that that index doesn't exist, and that algorithm's correct. We cannot do that with this algorithm. So compare and contrast what I have here with what we studied before. What we studied before had an invariant. We could rely on that invariant. This does not. There is no invariant. Now, I wasn't trying to trick you, but this is Jamie teaching. I was setting up your mind to learn something. If you actually type something in the comments as an invariant, awesome. All right, I can guarantee you got it wrong because this algorithm does not have an invariant. But what I was doing, and I do this all the time with my students, is I set up their minds to have a question in there. Remember, we're prepping those neurons with a hypothesis. And then, bam, I just punched all the neurons in your brain. You'll never forget this. For those of you who commented, awesome for you. I appreciate it. You'll never forget this, and you can compare and contrast what it means to not have an invariant versus what it means to have an invariant, because we have to have invariants in our algorithms, and we will continually use invariants throughout this playlist. Key concept: no invariants, no guarantees.